I'd like to welcome everyone to today's session here. We're going to be talking about a very difficult subject tonight, but I'd like to first start out with a couple things. First, I'd like to apologize for the last meeting. I had something that just wouldn't quit, some kind of an upper respiratory infection, and couldn't shake it. Hadn't had anything like that since high school or grade school. So we're all over that and better. Also, the next session after tonight will be on the topic of non-radiometric dating. Things like aluminum filling up in the ocean, salt filling up in the ocean, dust on the moon, and all these sorts of things. We're going to be looking at those and how they relate to the age of the Earth. And so that'll be something to look forward to. We're going to be looking at the Earth's magnetic field, which is arguably one of the most rigorously modeled items, although we're not going to get into all that modeling. We'll be discussing what the implications are for the creation model. Tonight's session, we're going to be looking at the most difficult topic called radiometric dating. And what we're going to be looking at is how radiometric dating occurs and what implications are there for the creation model of origins. Remember, we're here to discuss the creation model of origins and not necessarily kind of refute evolution that is so often done in these sorts of forums. So, let's take a look at some of the things that we want to discuss. We're going to look at some introductory concepts. We need to discuss and bring some things to the table so that we kind of understand the vocabulary that goes into this topic of radiometric dating. We're going to be looking at here we go. Oops. We're going to be looking at the decay of a free neutron. You might not have known, but neutrons do decay. We're going to look at the actual radioactive decay process. How does it work? The law that undergirds the radioactive decay process. And we're going to look at the creation model of origins and how does this impact our understanding of radiometric dating, and then we'll take questions from the floor. So let's take a look at some introductory concepts. And one of the things that we have to figure out is what in the world is an atom. And an atom comes from the Greek word atomos, and it literally is a compound word it's a compound word from temno, which means to cut, and then the Greek negation is the Greek letter alpha, or our modern English word letter A. So it's atemno, or atomos is the Latin form. And what this means is temno means to cut, and atemno means not to be able to cut down further. And so an atom is something that is indivisible, that cannot be cut down any further. So it is the most basic of constituent parts. So that is what an atom is. That's how the Greeks viewed it. And that is essentially how we're viewing it here today. In the atomic structure of an element, we have a nucleus, and in that nucleus are protons and neutrons. Surrounding the nucleus, we have electrons, and they are of a particular charge. So the number of protons determine what type of element it is. So for an example, carbon has 6 protons that we'll see. Nitrogen has 7. So it's the number of protons that determine what the element is. Okay. The number of neutrons determines the what we call the isotope of the element, and that is the guy that wants to become just a normal element. Okay, so the isotope is the type of element that will decay into what we might call a happy atom, if you will. It's the way we were told in junior high, that these atoms want to be happy atoms, and therefore they decay to a happy state. Now, the other important thing to remember is the chemistry of the atoms all take place within the electron layers. There's no chemistry that goes on in the nucleus. It's all in the chemical bonding and so on of the electrons. So again, a nucleus, or an atom, is made up of a nucleus, which is made up of protons and neutrons. The nucleus has surrounding electrons, and the protons are positive charged, and the electrons are negatively charged. Now, this is called the classical view of the atom. If we were looking at this from a quantum perspective, would have a different kind of way of describing things. But this is the classical view of the electron, and that's essentially what we're going to use for this session tonight. So let's take a closer look into the atom. And if you notice, in the nucleus, you see in the protons and neutrons, you see these little circles with bands connecting them. And the nucleus, of course, as we saw, is made up of these nucleons, protons and neutrons. And each of these nucleons is made up of what are called quarks and gluons. Okay? And a proton, for an example, is made up of 2 up quarks and 1 down quark. Okay? And you might expect that a neutron is made up of 1 up quark and 2 down quarks. And so you can tell immediately from this description of protons and neutrons that protons and neutrons are not they're not the basic atomic particle, that there's something smaller, that they're made up of something which are more fundamental, namely quarks and gluons. Gluons are the guys you might think that hold the nucleons together. They hold the quarks together. And so this is something new that you may not have learned in your chemistry or in your high school physics class many years ago. So electrons, quarks, and gluons are really the elementary particles, not protons and neutrons. So in our model here today, the elementary particles which are not broken down further, at least at our discussion level here, are the electrons, quarks, and gluons. Okay, a happy nitrogen atom. Let's take a look at an example here of a happy nitrogen atom. We have to review our high school chemistry and nuclear nomenclature, and I'm sure you all remember this. Here we see the symbol N for nitrogen, and the bottom number refers to the number of protons. The number of protons tells you what type of element it is, right? So you'll always have that number in the bottom. Then you have the number at the top to the left of the symbol. You have the atomic weight, which is nothing more than the sum of the protons and the neutrons. Now, what we're going to see tonight when we get into some of these heavier elements that decay, you might think all elements are, well, simply doubling one of the protons or one of the counts on the neutrons, right? If you have 25 protons, that means you're going to have an atomic weight of 50, right? Well, once you get to the higher masses, it doesn't quite work that way, and you no longer have 7 and 7 or 35 and 35. You'll end up very often having more neutrons than you do protons for various reasons beyond what we want to discuss here. So this symbol is made up of, the entire symbol is made up of the symbol N for nitrogen, the atomic number, which is in the bottom of the letter to the left, and the atomic weight, which is to the upper left. And this is the fundamental state of nitrogen, and it is called the happy state, if you will. So the happy state of nitrogen has 7 protons, and it actually has 7 neutrons in this particular case. So that is the happy state of the nitrogen atom. Okay? All right. So the atomic mass, of course, is 14 because it has 7 protons and 7 neutrons. And as we will see, the number of neutrons do not always match the number of protons. Okay? It does in this particular case, and it does in some of the lighter elements, but not in the heavier elements. All right, let's take a look at carbon, nitrogen and carbon, because we want to understand not only just the elements, nitrogen, carbon, bismuth, what have you, but we also want to understand their isotopes and what we mean by an isotope of carbon. Well, let's take a look. Here to the left, we have a happy nitrogen atom. It's made up of 7 protons and 7 neutrons. Okay, it has 7 electrons, of course, orbiting itself, and there we see the symbol. Next to it in the middle, if you take a proton away, you have 6 protons, and you take that proton and just make him a neutron. Okay, you make him a neutron and you lose an electron, and I'll tell you a minute how we can do that. You end up with an element that has 6 protons, but it has 8 neutrons. All right. Well, that happens to be carbon-14. Now, what happened to that electron? That electron formed with that proton and created a neutron, if you will. So the nucleus grabbed one of the lower electrons in the lower orbit and made a neutron. That's where we got that 8th neutron. It's called electron capture. We'll talk a little bit about that in a second. So here what we have in the middle, we have carbon-14. It's carbon because it has 6 protons, but it's an isotope because it doesn't have an equally balanced number of protons. So it has 8 protons. That's carbon-14. Carbon-14 because there are 4, it has an atomic weight of 14. Okay, so notice what the symbol is. The symbol is C. It has 6 protons, so it has an atomic number of 6, but an atomic weight of 14. So you might imagine that this atom wants to decay to get back into its happy state of 6 protons and 6 neutrons, right? Well, that's exactly what you see next to that on the right, the happy carbon-12 atom, if you will. And you can see there the carbon-12 has 6 protons, 6 neutrons, 6 electrons, and the chemical symbol then is a large capital C with 6 in the lower left and the atomic weight of 12 in the upper left. And so they're examples of isotopes. Okay, so an isotope is a state, if you will, of a particular element that's unstable. Carbon-14 is an unstable version of carbon-12, and so that isotope wants to decay into carbon-12. Let's take a look now at the decay of a free neutron and various types of nuclear decay. We're kind of going through this to bring us to a point where we can understand and bring this to a position where we can understand how the creation model can utilize these elements. A neutron decays in a particular way. There we go. The neutron decays into a proton and an electron and what's called an antineutrino. And this antineutrino, if you want to think about it, it's kind of like energy. And so this neutron, over a period of time, will decay into a proton and an electron and give off some binding energy, if you will. So that is how a neutron decays. Types of nuclear decay, there are a plethora of them. We have alpha, beta, and gamma decay. We have electron capture, which is nothing more than the bottom electron being absorbed by the nucleus, namely by the protons, and that one proton that's captured that electron becomes a neutron, if you will. Then there's proton decay, where a proton is ejected out of a nucleus and actually changes its elemental structure or elemental identity. A positron decay, where an electron with a positive charge is ejected out of the nucleus. That's kind of an interesting decay. Neutron decay, where a neutron is ejected out of a nucleus. Cluster decay, where a small nucleus is ejected out of the main nucleus, but something bigger than what's called an alpha particle or a helium atom, which we'll talk a little bit in a minute. So these are just some types of nuclear decay that physicists deal with daily in the laboratory. Let's take a look at alpha decay. This is probably the more important one that we want to talk about tonight. Alpha decay exists when the nucleus ejects an alpha particle, and this alpha particle is nothing more than a helium nucleus, 2 protons and 2 neutrons. So these 4 elements are ejected out of the nucleus. Well, when that happens, 2 protons are being ejected out of that nucleus, which tells you that the identity of the parent atom is changing, right? It's losing 2 of its identifying particles. Okay? So for an example, let's just, to make it easy, let's suppose a carbon atom ejected an alpha particle, as if that would happen. It's losing two protons. So it's going to change from carbon. It's no longer a carbon atom. All right? Let's take a look at uranium-238. Uranium-238 ejects a helium nucleus, a helium atom, an alpha particle, if you will, and it becomes thorium, which is what the little graphic there at the bottom shows. So when uranium-238 ejects a helium atom, it becomes thorium. Why? Because it's losing 2 of its identifying particles, 2 protons. Let's take a look at beta decay. Beta decay is nothing more than when a neutron in the nucleus ejects a beta particle, or an electron, along with some binding energy, if you will, called an antineutrino. So what happens in this case, the neutron literally turns into a proton. And a good example of this is the important medical. They don't use this therapy any longer. Several years ago, they went to a non-radioactive therapy, as I understand it. But iodine-131 is an isotope of iodine, and this is used in thyroid therapy. And what happens in this particular decay is an electron is shot out of the nucleus, or a beta particle. An example of beta decay is carbon-14. Okay, here we see carbon-14 and nitrogen, and an electron is given off, and an antineutrino is also resultant of that process. So that's beta decay, where an electron is given off from the nucleus. Let's take a look at gamma decay. This is when a high-energy photon, or a gamma particle, is given off out of the nucleus. Now, a particle is not given off, but a photon, a unit of light, is given off out of the nucleus. So the nucleus itself is in an excited state. Think about it as vibrating, and it shoots off a photon, and it kind of becomes less excited. So it gives off a gamma particle, and an example of this, of course, is plutonium-240, where if you notice on the graphic, notice the symbol. Plutonium is 240 over 94. Well, it gave off a gamma particle, but what is the chemical symbol. It's still plutonium-240/94. So it hasn't given off a proton. It's given off a photon. It's given off a little bit of energy, and it's no longer as excited as it was prior to giving off that electron. So it's kind of a way in which it's less agitated, if you will. Okay. So that's alpha decay, beta decay, and now this gamma decay. So let's take a look at the actual radioactive decay process and see how this works and how you and I might use this as we develop our creation model. So what happens here is an unstable atom will decay until it reaches a stable state. Okay? The initial atom is called the parent, and the next constituent part in the process is called the daughter. So you have the parent decaying into the daughter, and if this gal is still radioactive, she'll further decay and decay until they get down to a non-radioactive form. So the decay process follows the famous exponential curve, which we will discuss later. So the amount of stuff given off follows this exponential decay curve that we'll talk a little bit about here in a moment when we talk about half-lives and such. Types of radioactive decay processes. Well, uranium and lead. Uranium will eventually decay into lead through this decay process. Carbon-14 eventually decays. Potassium and argon. Potassium eventually decays into argon. This is used to date archaeological and more so not archaeological but geological structures. It has a half-life of 1.3 billion years, and it decays by electron capture. In other words, the protons in the nucleus capture one of the low-lying electrons, and that proton turns into a neutron. Rubidium-strontium, 47 billion years. In other words, the half-life of this material, it takes 47 billion years for half of it to decay from rubidium to strontium. Samarium and neodymium, this is 106 billion years. Lutetium and hafnium, 220 billion years half-life. And then rhenium and osmium, 40 billion years. This decays by alpha decay. So these are just some examples that physicists use in dating things, and that they have found are very helpful in looking at decay processes. Let's take a look, however, a little bit closer at the uranium-lead decay process. So we want to look at uranium-lead. Uranium-lead is used to date old-age rocks. Okay, and it's not used to date organic material. The reason being, you might expect, is presuppositional. If the half-life of uranium, the uranium-lead process, is on the order of billions of years, what might you conclude about organic material? It's not going to be around, right? 4.3 billion years. So this would not be theoretically a good method to date organic material. Therefore, uranium-lead is not used to date organic material. It's using present-day process rates, of course, and it's used to show ages on the order of 4.6 billion years. So if we assume, if our presupposition is that uranium has decayed similarly over the eons of time, then its half-life is 4.6 billion years. The decay sequence of uranium-lead is extremely complex, and we're going to look at that just to show you how complex it really is. But it begins at an unstable parent, and it continues to decay through many stages of unstable daughters. And this is what it looks like. I won't go through every one here, but you might see uranium-238, its first decay process is alpha decay. So it gives off an alpha particle, 2 protons and 2 neutrons. It's a helium nucleus, right? So a helium nucleus shoots out of the uranium nucleus, and it becomes thorium-234. Okay, it takes 4.5 billion years for half of the uranium material to eventually decay into thorium. That's what these dates here are. Okay. So again, if you jump down to the next occurrence of uranium, uranium-234 decays by alpha decay into thorium-230. Okay, this is the 4th step. So it eventually makes its way from uranium-238 to 234, then it decays by alpha decay again, and into thorium-230. And then you can see this complex sequence, and you can see that it only takes 27 minutes to decay through beta decay to give off an electron from lead-214 to bismuth-214, right? So this complex decay series is required for uranium-238 to decay into lead-206. And it takes roughly 4.5 to 4.6 billion years for that to occur. Okay, so that is the uranium-lead decay sequence. And notice, you've got decay sequences. You've got alpha decay, you have beta decay, and that's basically it. You don't have any electron capture or anything like that. So the uranium-lead sequence comprises alpha and beta decay. So an alpha particle is given off, and an electron is given off in these various sequences. So that's uranium-lead. It's kind of a complex sequence. Let's take a look at carbon-14. Now, carbon-14 is used to date organic material, bone, tissue, and so on. And the reason for this is because the half-life of carbon-14 is only 5,730 years. So what that means is that if you have a gram of carbon-14, 5,730 years later, you'll only have half of that amount left as carbon-14. So theoretically, you'll have carbon-14 and half carbon-14 and half carbon-12. Okay? And so if you have a bone, let's say that's been laying there from the time of the flood, roughly 23 to 2400 BC, that's about, almost 5,000 years from today, right? Maybe 4,500 years. So you're going to see some decay in that time period. So you'll be able to tell the life expectancy. Now, carbon-14 is created in the upper atmosphere through cosmic radiation hitting nitrogen atoms. Okay, maximum dates for this dating technique range to 75,000 years, and I believe some of the more sensitive methods are higher than this now. It has a very complex life cycle, as we will see here in literally a second. This is how carbon-14 works. The sun is giving off cosmic radiation. It hits nitrogen atoms and so on, and free neutrons are ejected. It hits the neutrons and forms carbon-14. Now, carbon-14 then combines with oxygen to form CO2 or carbon dioxide, but this particular form of carbon dioxide is radioactive. So this is radioactive carbon dioxide, and there's radioactive carbon dioxide all around us, even as we are sitting in this room. The animals eat the grass that is ingesting this radioactive carbon, CO2, and they eventually die. So as long as the creature's living, they're constantly eating this radioactive material. When you and I eat a salad, for an example, we're eating radioactive carbon. You probably never thought about that, but when you eat your salad tomorrow at dinner, you're going to be eating some carbon-14. Well, this creature here dies and he stops eating it. So that's when the clock ticks, according to the dating method, okay? So the clock's ticking, and this carbon-14 that is now stationary, theoretically, in this creature is ticking away. You know, if you come back to that creature 5,730 years later, only half of the carbon-14 that he ate at his salad the day he died is going to be there. Okay, so now you have a way of measuring when this creature died by measuring the amount of carbon-14 that is at the time when you measure, right? You just extrapolate back and you say, okay, this guy was 10,000 years old when he died, when he croaked. Is that really that easy? Well, we'll see that there are a lot of assumptions in there. But that is basically how the carbon cycle works. All right, now keep that in mind, and let's look at the radioactive decay law, because this is very, very important. Now, what I want to say in the outset is, if you're sitting in a high school or a college level physics class and you're presented this, you're being presented this. At least you should be told that this law that you're looking at is freestanding, if you will. It's independent of anything else around it. So when we look at this law, we're not taking into consideration its geological setting. You know, you've got a piece of uranium sitting in a strata somewhere, or a stratum, and it's decaying. But it's also being impacted by its surrounding material, right? Water's coming in, water's going out. So we're looking at this as if it's kind of a closed system. And what this law is saying is, on the ordinate or the vertical axis is the amount of radioactive material. Time is on the horizontal axis, the abscissa, if you remember your algebra. And the original amount, we'll say, it starts at P0. And so that's the initial parent amount. From the time the clock starts ticking, it slowly decays until the first half-life, when you have half of the material left. So if you come down the vertical axis halfway down and move over to the curve, that tells you, that gives you the time in which it takes for half of the material to decay. That's called a half-life. So when you have half of the original material left, that is the amount of time that it took for that to decay is called a half-life. And so you can continue that law, and from that particular point go down another half-life, or another half of material. In this case it would be a quarter of the original amount, and go over to the graph, and that will tell you the second half-life, okay? And so this is how the radioactive law works. It slowly decays over time, and the half-life, that 5,730 year number that we read for carbon-14, is the amount of time required for carbon-14 to decay into carbon-12. So this first half-life on the horizontal axis would be 5,730 years. Okay, the next one would be 2 times 5,730 years, 3 times, and so on. So this nice little exponential curve follows that pattern. Now let's take a look, and I believe this is the only equation we have in this particular presentation. In the middle of that graph, there is an equation, okay? And that equation says an awful lot. In fact, it has said everything I've just spoken. Let's take a look at, however, let's take a little bit of detail into this. That P sub 0, that is the initial amount that you start with, okay? And that little exponent that's being multiplied to P sub 0, e to the minus lambda t, if you will. That is telling you how fast the material will decay. And that little L here, or it actually should be lambda, that's the constant that dictates how fast the material would decay over time. Okay? So, in this law, there are at least two assumptions, and I'm going to add a third. Number one, the first assumption is that the lambda, the decay constant in the exponent, is constant over time. That's the first constant, the first assumption. Second assumption is that you and I can determine what the original amount is. In other words, from today, we can extrapolate back to the original amount and know that figure, okay? That's an assumption. And the third assumption that I want to add to this that everyone seems to forget is that this law, the way it is presented, is isolated from everything else. Okay, I haven't remarked about the fact that this little piece of carbon that we're talking about, or uranium that we're talking about here that's decaying this way, is sitting in a layer somewhere being impacted by water, by bugs, okay, by the surrounding material, by other radioactive material, okay? So we're assuming for a moment as we discuss this that it's in a closed system and it's not being impacted by anything else. Okay, that's an assumption. That's how you and I would learn this law in a physics class. Now let's take a look at this idea of a half-life. All right. This is a concept we need to understand very well to understand this concept of radiometric dating. As you can see on the left, on the upper left, you have the parent. And for sake of argument, let's say the entire piece of material that we're discussing starts off as a complete parent of some radioactive element. After one half-life, only half of it's left. Okay, the other half is no longer radioactive. It's now the daughter. The other half is still hot, so to speak, and it's still continuing to decay. After the second half-life, you only have a quarter of the radioactive material left. Okay, after the third half-life, you've got an eighth, and then finally a 16th. And after the fifth half-life, you only have 1/32 of material left. So you can see that if the half-life is very quick, is very fast, then the material can very rapidly decay from parent to daughter. You can also see that the faster the half-life is, the more advantageous it is for dating organic material. And so these elements that have huge, long half-lives, like uranium, lead, and so on, potassium, argon, are valueless, theoretically, for organic material. And this is why. There's no organic material left after billions of years. Okay. Here we have a radioactive decay system, piece of granite or what have you. You've got pieces of uranium, and they are eventually, through that complex machine that we saw, decaying into lead. So the parent contains uranium, and as the parent and daughter, lead. Okay. Question: has the system been closed over time? So if you're the field scientist, you have to verify that that system's been closed over time, right? Well, you would pass the test immediately if you said it was open. Is all the daughter a result of the radioactive decay of the parent? In other words, maybe somewhere during the process of this particular uranium atom decaying into lead, there might have been other pieces of lead here that you are erroneously counting with the actual parent of the decay process. Okay, so that has to be taken into consideration. Can we know the original amounts of the parent and daughter? Well, the answer to that is no. Okay, we cannot know that. But there's a way around that, okay, or at least seemingly around it, that we'll talk a little bit about in a second. All right, how do we determine the age of a specimen? Well, we do that through this, actually, that's kind of a simple equation if you're used to looking at things like this. But then on the other hand, there's a logarithm. And if you remember high school algebra, logarithms were not fun, right? But this is the equation that is used to determine the age of a particular specimen. So let's kind of examine this guy here. Let's take a look at the assumptions in this above equation. First assumption is the following: that the decay rate is constant over time. That little lambda there, the assumption is that it doesn't change over time. It's always the same value. Okay? So there's no variation in speed as to how quickly this guy is decaying from parent to daughter. Okay? The initial amount of the daughter element is known. Okay? That you and I can somehow extrapolate back into time and determine what that initial amount is. And finally, and what I consider to be more important than anything else, is that the system's been closed over time. So that means that whole element in the parentheses has been closed and unaffected by the environment. Okay? That means the daughter over time and the parent over time have not been impacted by anything outside of themselves. So this is the equation that is used to date specimens. Okay? Let's take a look at how the creation model deals with this. And I will admit to you now that the creation model is in the process of doing a lot of research in this area. As I'll point us to some of the research that's going on. So there is a lot of research yet to be done, but there is a lot of research that has been done, and that the creation model has gleaned much from. So here are some of the things that we need to deal with. The creation model and radiometric dating must deal with the inherent assumptions: has the system been closed? Are the decay rates constant over the life of the specimen? And can the initial amounts of the daughter and parent be known? Well, the answer is no to the first. Has the system been closed? There is no closed system. So the answer to that is, has the system been closed? The answer is no. Are the decay rates constant over time? We'll see in a moment that there's good evidence that that's not true. Can the initial amounts of the daughter and parent be known? And we'll talk a little bit about that. Some key research has been employed here in Pittsburgh through the International Conferences on Creationism. In 1986, key research has been peer-reviewed, published, and presented at the International Conference on Creationism. And so this is materials that, if you want to get into this more deeply, you can get through the bookstore. The second element, or the second set of research material that we may want to get our hands on is The Earth's Catastrophic Past by Andrew Snelling. This is considered an updating of the original Genesis flood published in 1961 by Morris and Whitcomb, and this is a very good book. The only problem I have with the book is that all the figures are in the back. It'd be nice to have the figures in the text when the figure is being discussed. It makes things a little bit difficult, but it's possible to get through. And then finally, what is very relevant to what we're discussing today is what's called the RATE project. And this, of course, stands for Radiometric Age of the Earth, and this is a 2-volume set. The blue book on the left is kind of an introduction to the material, and it describes the research project that this book set of materials was written around. So the first book is actually an introduction to the work that these scientists are going to perform, and then the book on the right, the orange book, is the actual research results of their work. And so it's a very valuable book, and we'll talk a little bit about some items that they have been discussing. This is another good resource, Answers Research Journal. This is an online journal. It's free to anybody in this room. These are peer-reviewed journals. The journal editor is Andrew Snelling, and it's sponsored by Answers in Genesis. I highly recommend this. In fact, I recommend all this material here, but this is nice because it's a journal form and it's constantly updated as papers are submitted and eventually admitted into the journal. And then finally, the Creation Research Society Quarterly. This is a long-standing journal from 1963. It's also online. You have to pay an annual membership for it. But every journal ever published from 1963 is available to you. Okay? And so this is another thing that I would recommend. All right. Now, having said all that, let's talk a little bit about these assumptions. So all some of the things that we're going to be discussing right now is talked about in these materials that we just looked at. Isochrons and the initial amounts of daughter and parent. It is a problem not knowing or not being able to get back to the parent or the original amount, right? It's impossible. It's path dependent, right? And you don't know what that path is. So there's no way you can get from the amount of material that you're measuring today and extrapolate into the unknown past and get to a reasonable amount and have reasonable knowledge that that's the correct number. If in the mathematics of the thing you can do away with these initial amounts, then you've achieved something, right? So the idea is let's forget about the original amounts and let's go with ratios. Okay. So how can the initial amount of daughter element be determined or eliminated from the method? And that enters isochrons. Isochron dating is based on the assumption that if one takes many samples from the same geological unit, then a graph of these data points should give the age of the unit. Okay. So the idea here is that let's suppose we have a specimen, uranium lead, and we take various samples, and you can see what we have here. You have these various samples, and if you graph them and plot the line like this, then you take that data and you curve fit a straight line to this data. Where that line crosses the vertical axis should be the original amount of daughter. Okay? So it's a way that you can get around some of this this problem with knowing the original amount, metrically speaking. And it follows this wonderful, simple y is equal to mx plus b curve, and so on. So this is what an isochron is. No change in time, stasis over time. Okay, and so this is what is done for radiometric dating. The problem with the isochron method that has been shown by creationists over the time. There we go. Steve Austin in 1988 or 1998 showed that in the carbonate basalt layers, the ages that they were measuring through this isochron method was completely discordant. Okay, that it didn't follow this nice straight line. So the determination of the original amount was problematic. Okay, that it couldn't be done. The whole rock potassium argon model in the isochron in the Somerset Dam layer was also found to be very discordant, and this was published in the 2003 ICC by Andrew Snelling. So what these papers are saying is that the line coming through the data point is not straight. It didn't give a good correlation with the data. Okay? So the isochron method in these particular cases did not work. Therefore, the original amount was not correct or didn't have to be correct. Okay? So there's a problem. Finally, in the Grand Canyon, there has been research performed using the isochron method that has shown isochron discordances, and this has been known since long before 1994 when Steve published this book, Grand Canyon Monument to Catastrophe. Andrew Snelling, isochron discordances and the role of inheritance and mixing of radioisotopes in the mantle and crust. And this is, of course, a paper that is found in the rate books that we were looking at. So the point of showing these is that this is peer-reviewed research that has gone on by creationists to discuss the discordances of this straight-line approach with these isochrons, okay? That it's not as clean as they want it to be. Mount St. Helens lava flow, which formed and cooled in 1986, was tested through the isochron technique in 1996 using potassium argon. Do you remember what the half-life of potassium argon is? Several billion years, right? It was found to have so much argon that it yielded an age of 350,000 years, yet the lava flow was only 10 years old. So what these things show is that this isochron method is suspect, perhaps, or it may need to be revisited. Lava flows in New Zealand, known to be 50 years old, yielded ages of 350 million years old. In fact, multiple samples yielded 133 million years old, 197 million, 3.9 billion years, and so this is hardly an isochron. So these data challenge the assumption that the system has remained closed, that the initial amounts of daughter and parent can be determined, and I think that's the point. So the isochron method needs to be re-examined. Okay. Let's take a look at something else here which is very interesting, and that's this idea of polonium halos. What is so significant of these things? What are they? A polonium halo is formed by an inclusion of polonium in material, and this polonium is decaying. And as it decays, it rips the material as it's moving through, that it's moving through, and it forms these halos, okay, these spheres. Well, when you cut these spheres open, you see these circles, okay, and that's what we see here. So the figure here on the right is actually a three-dimensional view, and the figure on the left is a piece of that's been cut. Okay. Now, if you notice the sphere, we have three of them here, and the radius of each one of these spheres is proportional to the energy that the element is decaying at. Okay, so the particle that's being given off the radius is proportional to the energy of that particular particle. Now, the significant thing about this is that the inclusion, this polonium inclusion that is in the middle of the sphere, has to get there before the material is solid. Otherwise, it couldn't get there, right? So it's there before it solidifies. The halo can only form when it's solidified, okay? And some of these polonium halos have a very short half-life. 3.5 seconds for polonium-218, polonium-214, 164 microseconds, polonium-210, 138.4 days. So, do you see the problem? In order for these polonium halos to be photographed in this material, the inclusion has to be there. It has to get there when the stuff is moist and fluid, and the material has to rapidly cool to photograph those spheres in the material. Okay, it's not something that can take place over long periods of geologic time. If that material, this granite, if it was slowly cooling over time, these polonium halos would never occur. They have to be photographed very quickly, so to speak. That material has to quickly cool the moment that inclusion gets there. Okay? So that's the interesting problem about polonium halos. Gee, I hope we can see this. Okay. The radius of the decay circle is proportional to the energy of the decay process. So the longer, the bigger the radius, the bigger the energy that's given off by the particles. And so you can literally measure, you can literally determine by measuring the radius of each one of these spheres which element decayed to produce that sphere. It's really a remarkable thing. Okay? Now, creationists have identified many of these polonium halos in creation rocks. Okay, rocks that were formed on creation day. And that's reasonable to assume. God creates the rock, the polonium is there in the middle of the thing, and it's cooled like that, and it photographs the decay of these elements. Okay? However, okay, polonium halos have been found in granite from both creation week strata and flood strata. Now think about that, the implications to that. That means that the decay rate of polonium had to accelerate during the flood. And this is what the guys are working on right now at the rate group. So for the halos to occur, much more decay must take place than the average half-lives allow in order to get these nice solid rings. So a massive amount of radiation had to occur, decay had to occur, in order to photograph these spheres in the granite rock. Okay? And so what Eugene Chafin and the rate group are doing is they are coming up with quantum mechanical models to allow for rapid decay of these polonium halos, or polonium. Okay? So this suggests faster decay rates in the past, and in particular, those rocks that we know for a fact were laid down during the flood. Okay? You can understand during creation week because everything is supernatural, right? But we tend to think of the flood as something being, as a process that is purely natural. God might have caused it supernaturally or allowed it supernaturally, but then after that it all took place in a very natural, physical way. So there may in fact be a physical way in which decay rates can accelerate. So this is an area, see, the beauty about the creation model is here we have this evidence in the geologic column of a rapid decay of polonium in flood rocks. So that's driving the creation researchers to come up with new physics models of atomic decay, nuclear decay. So it's something that drives you to further theory and further modeling. So I think that's very good. So we have two places in time where polonium halos would have been formed during creation week, and then 1,656 years later, during the flood, these polonium halos would have occurred. Okay, so polonium halos have been found in granite from both creation week and flood strata. And you can see this in Andrew Snelling halos in multiple sequentially intruded phases of the Bathurst batholith in north-southwest Australia. Evidence for rapid granite formation during the flood. And this is a remarkable paper. Go home tonight and read it. It's really rather remarkable. And that's just published. So this is right off the press, March 2014. It's less than a year old. Evidence of rapid decay in flood rocks. That's really fun. Here's some more. In 2008, radio halos in the Shap Granite Lake District in England. Evidence that removes objections to flood geology in the proceedings of the 6th International Conference on Creationism. That took place right here in Pittsburgh. And here are some more. So you can take a look at some of these things later. Now, let's take a look at carbon-14. This is one of my favorite topics because I believe the paper that we're going to be talking about remains unanswered. Okay? A gentleman who I met through the ICCs, Robert Whitelaw, he was a nuclear engineer, I believe, out of Virginia. He published a paper in the Creation Research Society Quarterly in 1970. The title of the paper is Time, Life, and History in Light of 15,000 Radiocarbon Dates. What Mr. Whitelaw did at this time was he took all the carbon dates at that time. There was only 15,000 of them. Now there are 1 million of them. He took all these dates and categorized them and then normalized them within a young Earth creation model. So he took these dates that might have been 50,000, 100,000, whatever the times were, normalized them into roughly a 10,000 year period, and categorized them in 500-year chunks. So he took the data and categorized them in 500 years chunks. And what's fascinating about this, when he normalized the data, it took on a unique shape. Notice how the data here actually fell into place. What this is saying is this, that the number of carbon dates, that is the number of things that died and were found, from creation, not too much, right? But as time built up, things began to die and were found until the flood, where there was massive death, a massive event of extinction, and lo and behold, we have this massive jump in the elements of radiocarbon dates. Okay, so there are a lot of data here for the time of the flood, and then right after the flood, there wasn't as much extinction, and it began to creep up until modern day. So the graph shows a gradual extinction until about 4,000 years before the present, and that correlates to the flood. Mass extinction event at about 4,000 BP, before the present, and that, of course, would correlate to the flood. Extinction gradually increases after the major event. European and African data shows larger amounts of extinction just after the flood. Perhaps speaking of the Golden Age, remember several sessions ago, we talked about this Golden Age that took place after the flood. Few creationists talk about it. And I'm not sure why, but apparently, right after the flood, there was an environmental golden age where everything rapidly grew, animals rapidly went throughout the earth and so on, and this would be evidence for such a thing. So to me, Robert Whitelaw's paper is yet unanswered. It's just a remarkable thing. And this particular chart is actually a composite of both animals and plant life. In the original paper, however, he has separate graphs to show these two types of life. He also has separate graphs to show the geographical extent from around the places of Africa and Europe. So as you go out further from Ararat, so to speak, the ages, I should say it this way, as you get closer to Ararat, the radiometric dating, the carbon-14 dating ages get older. And you would expect that, right? That's where civilization started, according to the biblical record. It's a fascinating paper. Whitelaw's paper shows catastrophic extinction at the time of the biblical flood. By normalizing the data, additional information is gleaned. Research shows that the free decay model requires a framework of interpretation. And this is why I mentioned when we looked at the free decay model, this exponential curve that we looked at, where your teacher might tell you how radiometric dating works, how radio decay works through this exponential graph, right? What they're not telling you is that graph is being isolated out of its surroundings if you're talking about a geologic structure. If all you're trying to teach is how an isolated piece of uranium decays, that graphic is fine. Nice little simple linear first order differential equation. It's a real simple thing. But once you put it into a system of layers of dirt and rock, it's no longer isolated. That curve no longer works. Okay, it's changed. Especially uranium. Water comes in, water comes out, takes uranium out, puts uranium in. Okay, so it's problematic. So the point being is that when we look at these various methods of radiometric dating, we need to understand the presuppositions that are being brought to bear on the environment and the presuppositions that are being brought into the way they're modeling themselves. So when you talk to someone about the radiometric dating, ask them, well, okay, can you reassure me that the constant has been, that the decay constant has in fact been constant over the period of time that you're discussing? Are you sure you can determine what the original amounts were? We just saw several examples where they're not. And can you assure me that the system has remained closed over these millions and perhaps tens of thousands of years? And of course the answer to that is no. But the point being is that when you and I take this random data and normalize it into a creation framework, suddenly, as we see with Whitelaw's paper, the data takes form and it takes meaning now. Okay? And that's what the creation researchers are trying to do now through the rate group and others. So, having said that, let's open her up for questions and see what is on our minds. Yes.